Welcome to the 2020 SSC Pierre Robillard address. Before passing to Julie Atherton, who was chair of the Robillard Award Committee this year and had been scheduled to chair this session at the conference, I'd like to say just a few words around organization.
Thank you, Bruce. Zhang was awarded this year's Pierre Robillard Award for his thesis entitled Multiply Robust Empirical Likelihood Inference for Missing Data and Causal Inference Problems. His thesis was written while Shixiao was a doctoral student in the Department of Statistics and Actuarial Science at the University of Waterloo under the supervision of Doctors Pei-Sung Han and Shangbao Wu. His main focus was in applying important techniques such as empirical likelihood and calibration methods to improve estimation efficiency and robustness against possible model misspecification. Previously, Shixiao earned his BSc degree in statistics and mathematics from the University of Hong Kong in January 2014 and an MA degree in statistics from York University in July 2015. Currently, Shixiao is a postdoctoral research fellow at the Fred Hutchinson Cancer Research Center in Seattle, where he is working to develop individualized treatment rules using statistical learning techniques. Please join me in extending a warm welcome to Shixiao today. So I'd clap normally, but thank you, Shixiao.
Thank you, Julie. Let me first share my screen with you guys. Can you see it right now?
Yes, it's coming through clearly. Thank you.
Okay, thank you. And thank you all for tuning in for this talk. And I wish everybody stay safe and healthy during these troubled times. And it is really my great honor to be presented with this award. And I must thank Statistical Society of Canada for this great opportunity. So today I'm gonna talk about some major works I've done during my PhD study entitled Multiply Robust Inference for Causal Inference with Missing Data. And of course, this is joint works with my supervisors, Pei-Sung Han and Shangbao Wu. So to give an overview of what we have done, so my research mainly focuses on missing data and the causal inference problems. The major statistical tools we've been using, one is called empirical likelihood. This is a very famous non-parametric analogy to the likelihood methods. And another important tool we are using is called calibration. So calibration originated from survey sampling literature, but it has been brought to a lot of attention among other areas. So our goal is to trying to develop some semi-parametric methods for those quantities of interest. And the most important contribution of our works is this concept of multiple robustness. So for those who are familiar with missing data, you have this famous double robustness property, where you can have one model for the missingness probability and another model for the outcome regression, and the results are valid as long as one of the model is correctly specified. So this our multiple robustness concept extends that double robustness property, where you can have multiple models for the unknown quantities, and later on you will see. So this work mainly focused on the so-called pre-test, post-test studies. So subjects are measured 2 times, both at the baseline prior to the treatment assignment, that's called the pre-test measurement, and at the end of the study after the treatment assignment, that's called the post-test measurement. In this talk particularly, I will talk about 2 quantities we are interested in. The first quantity is average treatment effect. This is one of the most commonly used measurement of treatment effect in causal inference. So basically, it is the difference in change of marginal means of the potential outcomes between the two different groups. And the second quantity we are interested in is some kind of more recent quantity. It's called a chance of a longer survival. Basically, it is the probability that a patient in the treatment group can survive longer than a patient in the control group. Before I get into the methods, let me show you two motivation examples that why we are trying to consider such studies. So in the first example, we are looking at this ACTG data. It is a randomized trial that's trying to evaluate this new treatment monotherapy versus the traditional combination therapy for HIV patients. And at the baseline, certain baseline characteristics are measured, for example, their age, their gender, and among other characteristics. And after the baseline, you have treatment assignment. And then at the end of the study, which is this 96 plus minus 5 weeks, we measured their final outcome, these CD4 counts at the end of the study. So in this particular study, the problem here is some of the final outcomes are missing. And on the other hand, you have, luckily in this study, you have a randomization, but randomization is not always feasible in practice. So when you have observational study, you have to adjust the propensity score for the treatment assignment. In the second motivation example, we are looking at this international tobacco control survey. In this case, it's the other way around because you have a non-randomized study. We are trying to evaluate this so-called mode effect in data collection. So we try to see if there is a difference between using online survey versus using the traditional telephone survey. So you see the issue here is this treatment assignment is not randomized anymore because the participants have the choice to make to participate either the online or the telephone surveys. But in the same sense that the post-test outcomes, their response can be missing as well, similar to the previous example. So basically you have two kinds of missingness you have to adjust. One is due to the observational study, that's the treatment assignment, and the other one is the actual missing values you have for the final outcome. So let's move on to the first part. We are trying to evaluate the average treatment effect. So our contribution is to propose a dual method that can be used for both testing and the estimation of the average treatment effect. And the setting we are considering is the most general setting, that is a non-randomized pre-test, post-test study with missing data as well. So again, the proposed method is most importantly multiply robust to model misspecification because you can have multiple working models for all those unknown quantities, and the results are valid if a certain combination of these working models are correctly specified. First off, let's look at the data structure first. So for a sample of size n here, at baseline, you have some baseline covariate z. So this z is measured for everybody in the sample. Then after baseline, you have a treatment assignment t. So without loss of generality, I assume the first N1 subjects are assigned to the treatment group and the rest are in the control group. Then after treatment assignment, everything should be treated counterfactual. And before the end of the study, you can also have some intermediate covariates, but these intermediate covariates are counterfactual, meaning that X1 is only observed for the treatment group and X0 is only observed for the control group. Then this double yellow question mark represents the counterfactual missingness where you do not observe in the actual world. Then at the end of the study, you have these potential outcomes Y1 and Y0. They are also counterfactual, so you also have this counterfactual missingness here and here. In addition, we allow the actual missing values for each of the potential outcomes, meaning that in the treatment group, you only observe the first N11 subjects in the treatment group. And this single red question mark represents the actual missing values of these potential outcomes. Then later on, you will see you have to adjust these two layers of missingness to derive a consistent estimator of the ATE. We also made this common use assumption in causal inference. So assumption one is called no unmeasured confounders. Basically, you assume the treatment assignment only depends on the baseline covariates. For the second assumption is missing random. Basically, you are assuming the actual missing values of the potential outcomes only depends on the baseline covariates and their corresponding intermediate covariates. And you have this usual positivity assumption you always impose in causal inference. So we are looking at this average treatment effect, which can be expressed just in this way. It is the difference between the marginal means of these two potential outcomes. So you see we have three unknown quantities. The propensity score of treatment assignment, I denoted as pi z. It only depends on z because we have no unmeasured confounders. And you have two missingness probabilities for each intervention group. And I denoted as omega t here. It depends only on z and x. And you can also model this outcome regression for each intervention group. That is the expectation, conditional expectation of y given z and x. So later on, you will see how we can use multiple working models for each of these quantities and derive a consistent estimator and a test for the ATE. So let's start with the simplest case. Let's assume you only have one model for the propensity score and one model for the missingness probability. Let's forget about the outcome regressions for now. So if these models are correctly specified, then immediately you can consider this IPW inverse probability weighted estimator for the marginal means respectively. So I purposely write out the weights WI hat and the VI hat here as uniform weights, because later on you will see how they fit in into the empirical likelihood framework. So because these models, this pi model and the omega models, we assume they are correctly specified, then you can immediately construct this consistent estimator for the ATE. You just take the difference between these two estimators for the marginal means. So you see these, I write out these uniform weights. They are actually fit into this standard empirical likelihood framework because they are the maximizer of this so-called joint empirical likelihood function subject to these constraints. So these are standard normalization constraints for the empirical likelihood probability mass. So this gave us a way to construct an empirical likelihood ratio test for the ATE. The intuition to construct the empirical likelihood ratio test is that we will consider two sets of weights. So these weights, WI and VI hat, they are considered as the global maximizer of the empirical likelihood function subject to some constraints, then these weights can give you the consistent estimator for the ATE. And under the null hypothesis, we will consider another set of weights, those W and V's, but with tilt. They are considered as the restricted maximizer of the yield function. And they will subject to the same constraints you used here for the estimator, plus one additional parameter constraint involve the null hypothesis directly. And this will give you the empirical likelihood ratio statistic. To be specific, our goal is to consider this test delta equals to a certain given value delta star. For example, if you want to test if there is indeed exists a treatment effect, that corresponds to testing delta star equals to 0. So the intuition is to find the discrepancy between those two set of weights. So how we are going to construct those restricted maximizer, we just have to impose down an additional parameter constraint for those for the optimization problem. So these restricted maximizer Wi tilde and the Vi tilde, they are satisfying all these constraints here. They are maximizing this joint empirical likelihood function subject to these normalization constraints, in addition of these so-called parameter constraints. So on the on the left-hand side, you see it takes the form of the IPW estimator, the difference of the IPW estimators. And on the right-hand side is just the value you want to test. So the idea is, if the null hypothesis is true, that delta indeed equals to delta star, then this restricted maximizer should be close to the global maximizer you use to construct the consistent estimator. Then the discrepancy between these two set of weights gives you a measurement of the deviation from the null hypothesis. Then we can immediately construct this empirical likelihood ratio test statistic. We measured the discrepancy of the two set of weights respectively by their ratio. And this is very standard empirical likelihood construction for two sample problems. Then if these models are correctly specified, we can show that under the null hypothesis, this test statistics follow a scaled chi-square distribution. And there's a scaling constant in front of the chi-square. I will not go into the detailed expression, but in this way, you can construct the empirical likelihood confidence intervals. So our goal is to improve robustness against the model misspecification. Previously, you only have a single model for pi and a single model for the missingness probability. Let's move one step further, that you still have a single model for the pi model, but you can have multiple models for the missingness probability. And starting from now, I will consider this new estimator. It is the difference between the weighted average of the observed outcomes. So the idea is similar to before. You will consider two set of weights. Those with hat will give you a consistent estimator, and those with tilde will be used to construct the empirical likelihood ratio test statistic. So let's assume you have JT number of working models for each of these missingness probability. So the global maximizer, the W and the V hat, they should be the maximizer of the empirical likelihood function subject to these normalization constraints, and all these two set of new constraints. You see, these new constraints are involving the multiple working models for the missingness probability. Basically, you have J1 number of constraints for the treatment group and J0 for the control. But the beauty here is the resulting estimator is so-called multiply robust because this estimator here is consistent if the pi model is correct, and only one of the multiple working models for the missingness probability to be correctly specified. So this improves the robustness against the model misspecification. You can throw in multiple working models for the missingness probability. And actually, these constraints are not coming out of nowhere. They are actually this the data version, or you can call it the empirical version of these moment conditions, just by taking these particular h and h1 and h0 to be these two different functions. And this is actually the idea of calibration. Calibration is originated from survey sampling in order to bring in more information to improve estimation efficiency. And indeed, this is the moment condition for our calibration constraints. To construct the empirical likelihood ratio test, we just have to impose one additional parameter constraint to construct those restricted maximizer. And again, here, the additional parameter constraint on the left-hand side, it is in the form of the estimator, and the right-hand side is the value you want to test. So the idea is still similar to the previous one, that if the null hypothesis is true, then this restricted maximizer should be close to those global maximizer. And this resulting empirical likelihood ratio test is also multiply robust in the same sense as the estimator. That is to say, when the pi model is correct, and one of the multiple working models for the missingness is correct, then the resulting empirical likelihood ratio test has a scaled chi-square distribution. So now you can have multiple working models for missingness probability, but how about the propensity score? You can also impose multiple working models for the propensity score, but that really complicates the procedure, that you have to split the procedure into two steps. So in the first step, you want to construct some other ways that basically mimic or you can say consistently estimate the true propensity score. Then in the second step, you just use a similar procedure to the previous one by taking the true propensity score model as the weights you constructed in the first step. So for the first step, you consider another set of weights, Pi and the Qi. They are the maximizer of this particular empirical likelihood function. You see, this is different from the previous one because these probability mass are directly imposed on all the subjects in the treatment and the control group respectively. And again, they are the maximizer of this function subject to the normalization constraint, and all these constraints based on the multiple working models for the propensity score. And actually, these constraints are not coming out of nowhere as well. Again, it is the data version of this particular moment condition by taking the each function to be the multiple working models. And again, this is the idea of calibration constraints. So, but we can show that if one of the multiple working models for the propensity score is correctly specified, then these two quantities here are actually asymptotically equivalent to the actual true pi and the 1 minus pi for each group. And whenever you construct the weights, the W's and the V's, you can just replace these pi and the 1 minus pi in the previous procedure by these new quantities here. But the robustness of this resulting estimator is even stronger because it is the estimator is consistent and the test is valid, and it only requires one of the pi model and one of the omega model to be correctly specified. In this way, we really improve the robustness against the model misspecification. Up to now, I haven't talked about the regression models, but indeed you can also have multiple working models for the outcome regression as well. So for example, you have KT number of working models for this conditional, for this particular conditional expectation. Then whenever you construct the W's and the V's, you can just throw in this two set of additional constraints based on the multiple working models. And again, they are actually the data version of those previous moment conditions we are using by taking the functions to be A1 and A0. But the robustness here is even stronger because the estimator is consistent and the test is valid as long as one of the pi model is correct, one of the omega model, or one of the outcome regression models to be correctly specified. So here, let me show you a little bit of our simulation study to demonstrate the numerical performance of our proposed method. So in this particular simulation, at baseline, we generate this uniform random variable Z, and we used a logistic regression for the treatment assignment. We considered different true values of the treatment effect. You can have no treatment effect, or you have positive treatment effect. And for the missingness probability, we consider two logistic regressions for each intervention group. I won't give you the detailed construction, but just bear in mind how we set up this simulation. And for each of these three unknown quantities, we imposed two models for each of them. For example, for the pi model, you can have a logistic regression with covariate Z square, or you can have a C log log regression with covariate Z and exponential Z. And similarly for the other two quantities, just bear in mind that those models with superscript 1, the models in red, they are actually the correctly specified model. So later on, whenever you see superscript 1, you will know this is the correctly specified model. So let me show you the results of the test first. Here, I only show you the particular results based on using these four models. Here, I used both of the pi model and both of the missingness model to construct the empirical likelihood ratio test. And we are testing delta equals to 0. So when delta is indeed equals to 0, you can see the empirical likelihood ratio test preserve a appropriate type error here. And the 95% coverage confidence interval have a very nominal, have a very good coverage probability to the nominal level. We also compare this yield ratio confidence interval to this wall type confidence interval based on the asymptotic normality of the estimator. But the wall type confidence interval is not performs not as good as the empirical likelihood ratio method. And this is well documented in the empirical likelihood literature that the empirical likelihood methods are data adaptive, and it can have a better performance, especially when the data distribution is skewed. When the true treatment effect is not 0, you can see again the yield confidence intervals have a better coverage probability than the wall type confidence intervals. For the estimation part, let me explain a little bit this table. So in the first row, you have these pi models. For example, here in these two columns, I only used the correct model for the propensity score. here is I use only the incorrect model, or I can use both of the models. And we compare our multiply robust estimator to the inverse probability weighted estimator and the AIPW estimator commonly used for missing data. And when the pi model is correctly specified, actually the multiply robust estimator perform very similar to the IPW and AIPW estimators. So these estimators in red, they are theoretically consistent. So you can see they have very small relative bias. But our estimator can accommodate not only one, but multiple working models at the same time. For example, here, you can use both models for omega and A. And our multiply robust estimator can also accommodate both models for the performance score as well in these two columns. And even more interesting observation is that when the performance score model is incorrectly specified as in these two columns, none of these estimators is theoretically consistent. So they all have very large relative bias and poor efficiency. But comparing to the IPW and AIPW estimator, the multiply robust estimators perform much better. So this kind of phenomenon is well noted in recent literature for multiple robustness literature, because this is the purpose of using calibration constraints. By using that calibration constraints, somehow the constraints captured the relationship between the final outcome and the baseline and the intermediate covariates. That contributes to reducing the bias and improve the efficiency of the resulting estimator. So to summarize, in this first part, we propose a method that is a unified inference tool to both testing and estimation of the average treatment effect. And we can accommodate multiple working models for each of these unknown quantities. And this study is very general. We consider a non-randomized study with missing data as well. So let's move on to the second part, which you are interested in the chance of a longer survival. So basically, sometimes instead of the ATE, you want to test the equality of the survival functions of the two different groups. So you want to see if the survival function of the treatment is stochastically greater than that of the control group. And for this test, actually you can reduce it to test this particular theta 0. Here, it is the probability of Y1 greater than Y0. So you can, we call it the chance of a longer survival. And if this hypothesis, if the survival functions are indeed equivalent, then this particular parameter should equals to a half. So testing this equality of the survival functions can be reduced to test this particular parameter equals to a half. So if there's no missing data, there is a famous non-parametric test. It's called the Mann-Whitney test. So basically, this is a U statistic. It is just a generalization of sample means. So you take the sample means of these particular indicator functions, comparing these two groups. And under this null hypothesis, this test statistic follows a standard normal distribution, so that you can immediately use the wall type test to construct confidence intervals and to test if theta 0 equals to half. So previously, you see we used these W's and the V's for constructing the estimator for the ATE. And indeed, actually, we can immediately use these W and V's to construct a multiply robust estimator for this particular parameter. You just take the weighted average of these indicator functions to estimate this particular theta. And this resulting, we call it the multiply robust Mann-Whitney test statistic. It is multiply robust in the same sense to the previous estimator for the ATE that I will repeat here. It is the result estimator is consistent if one of the pi model is correctly specified and one of the missingness model or one of the regression model is correctly specified. And we can immediately construct this multiply robust Mann-Whitney test that under the null hypothesis, this particular test statistic follow a normal distribution, and immediately you can construct this wall type confidence intervals for theta. Let me quickly show you a little bit simulation study. We generated the data similar to the previous simulation for the ATE. And under the null hypothesis, you see here all of the estimators preserve a proper type prime error here. And when the deviation from the null hypothesis moves away, the power of the test increases. So all the estimators here are consistent due to the inclusion of pi 1, omega 1, or A1. That's basically what we've done for this pre-test, post-test studies. But before I finish, I want to talk about a little bit about some ongoing and future works we are looking at. So you see the major tools we've been using is one is called empirical likelihood, and the other one is called calibration. So calibration is originated from survey sampling, but it really brings up people's attention because by using calibration, you can achieve a lot of desirable properties such as multiple robustness, global efficiency, intrinsic efficiency, a lot of desirable properties. And currently we are working on this review paper with my supervisors to see how we can connect the calibration idea among different areas, particularly from survey sampling to missing data and causal inference. And hopefully we are trying to bring up the awareness of the importance of calibration methods. And particularly in causal inference, there is a particular property people are very interested in, that's called the covariate balance. So there has been a lot of development to achieve covariate balance, but a lot of them can only achieve covariate balance asymptotically. But by using calibration, you can achieve exact finite sample covariate balance, meaning that the exact three-way balance among the treated, the control, and the combined group. And there has been already some of the development using calibration in causal inference. These references, they may not be particularly used to achieve covariate balance, but indeed by using calibration, the covariate balance is automatically achieved. And nowadays, people always talk about big data and meta-analysis. So the goal is to combine different data sources to improve efficiency and to achieve estimation consistency. And indeed, calibration can contribute as well. And there are a lot of very recent development by using calibration to achieve these desirable properties. And hopefully in the future, we can we can develop some more important work using calibration. Okay, I think that's pretty much I want to say today. Thank you all very much.
Okay, I think now Robert leads the question and answer section.
Yeah, so I'll just say a word to participants. So if you have questions, if you could send them into the question and answer session window, and by default, Robert will pass those along to Shixiao. And if there are not too many, you can unmute and ask your question directly. So we'll just give a minute to see if any questions appear.
Okay, give it a couple more seconds to see if anyone asks questions. If not, I'm going to ask one myself. I wanted to ask about one of your future work slides. I think you had, it was this one.
This one?
Yeah. So I guess this is perhaps unfair because you're listing this as future work. You haven't thought about this, but maybe if you could talk a little bit more about what you mean, what covariate balance means in this context, and why this three-way balance is a desirable goal.
So basically, by covariate balance here, I mean for example, the distribution of the covariate in the treatment group should be equals to the distribution of that from the control group, right? So the three-way balance here, I mean the distribution is the same not only among the treated and the control group, but also is the same as to the combined group. And by exact finite sample covariate balance, I mean you achieve this kind of balance not asymptotically, but with finite samples.
Okay. Okay. Thank you.
Yeah.
We now have some questions coming in from the audience. I wonder, well, I'll read the first question, and then if someone else can unmute Richard, if there's any follow-up, we can do this interactively. Richard Lockhart asks, why was the root mean square error lower when you added a wrong working model to the right working model? And he says, not sure what slide that was, but fairly close to the end.
This one?
You should be able to talk now, Richard, by the way.
Maybe. I think that's it. It looks to me like the right-hand column RMSEs are generally perceptibly lower than the ones under pi 1. And what seems to have happened is that in addition to using the correctly specified propensity score model, you've added a wrong propensity score model, and somehow that's improved things. And it's, do you have any comments on why?
Yes, actually, this is not a universal phenomenon, but that's the beauty of using calibration constraints, because as I said, by using those calibration constraints, even you impose a wrong model into the constraints here, you can also, you still guarantee the consistency, but the additional constraints you bring in somehow captures additional information between the outcomes and the covariates. I think that contributes to the improvement of the efficiency here.
Thanks.
But this is not always the case, I believe.
Okay.
Thank you. Okay.
Thank you.
So the next question comes from Grace Yee. And she wants to know if you've thought about how you would incorporate censoring in your second in your pre-test, post-test survival function, your second problem?
Here, yeah, we haven't thought about that yet, but I believe we can incorporate censoring here, and I believe you can also have some form of multiple working models for the censoring probability. Actually, right now I'm working on something related to that kind of problem.
Grace, do you have any follow-up? I think you should be unmuted now. Or you, yeah, now you are.
Oh, okay. Yeah, thank you for a very interesting talk. I think when you introduce censoring, would you need to sort of modify your framework somehow? Because I mean, like in some of your development, you focus on using those inverse weighting technique, which is pretty much under the framework of estimating equation
Yes.
approaches. So I guess, yeah, I mean, yeah, any source would be helpful, yeah.
Yeah, I think the when you have censoring, you can also use the inverse probability censoring weighted version of that estimator, and I believe we can develop some kind of procedure here to accommodate the censoring as well.
Okay, yeah, thank you.
Yeah.
All right. Actually, while we have this slide up, this is more a question for clarification, Shixiao. I just the alternative hypothesis here. So the null is that the survival functions are equal. The alternative is that I want to make sure I understand what y is here. Is y and is this? Sorry, go ahead.
Y is just any number. So basically, we are trying to, you can drop these y's here. Basically, you want to see if one of the survival function is stochastically greater than the other one.
Right.
Okay.
So I'd just like to welcome everyone and congratulating Xiao with me. And I've kind of been fumbling around to figure out how we could clap. I don't know if anyone knows, but I'm going to clap. So thank you and congratulations again. Thanks.
So I'd like to just close by saying also thank you very much, Shixiao. And I'd like to thank everyone for attending. And please have a look at ssc.ca for some additional events which are scheduled around the conference. There are several workshops coming up. So thank you again and take care, everyone. Bye-bye.
Thank you.
Bye. Thank you all very much.